Hello, everybody. Welcome to today's Astroparticle seminar. And this will be the last one of the year. We'll resume early next year. I'm very happy to introduce you to today's speaker, a good friend of mine, and also known to many of you, Professor Katie Auchettl from the University of Melbourne. Katie did her PhD at Monash University. Then she was a postdoc at the Center for Cosmology and Astroparticle Physics at The Ohio State University. Then she came here. She was an assistant professor at DARC and NBIA, and she's currently both assistant professor, associate adjunct professor at UC Santa Cruz, and senior lecturer at the University of Melbourne. Katie works on many different topics, including stellar binaries, core collapse supernova, type 1a, type 1b supernovae, supernova remnants, pulsar wind nebula, and TDEs, tidal disruption events. And she specializes in the high energy emission from these objects, and her work combines the data analysis coming from observations and interpreting those data. She's done extensive work on TDEs, including a detailed study of particular candidates, like building a comprehensive catalog of TDE candidates, telling TDE emission apart from AGN or imposters, and studying the cosmological evolution of the TDE rate. And today we're gonna hear from her about understanding the multi-wavelength properties of bright and nearby TDEs. So Katie, thank you, and please take it away.
Awesome. Thank you so much, Maurizio. I think that was one of the best interviews I've ever, introductions I've ever had. So that's kind of amazing. So as you could see, thank you so much for letting me be able to give this talk today. But as you see, I get to work on a large number of different exciting things. But today I'm going to talk to you about one part that I really find exciting, and it's particularly understanding the multi-wave properties of tidal disruption events and how you can actually kind of differentiate them from other transients and also use them to kind of probe a wide range of properties related to the black hole itself and even the star that's being disrupted. But of course, before getting into kind of all that exciting part, let's start off from the very start, right, to get the background knowledge about this. So black holes with masses greater than approximately 10 to the 5 solar masses have been shown to reside at the heart of most galaxies, much like Sagittarius A star, the supermassive black hole at the center of our own Milky Way. And while this black hole is close enough to us that we can actually study its properties and influence on its surroundings directly, most black holes are located much further away from us, which makes it actually more difficult to apply the same techniques we use to study the properties of this object. And so as a consequence, a major question that we have in modern day astrophysics is essentially what is the properties of the black holes in our universe as a whole? But why are we interested in these sources? Why are we apart from black holes being cool, what particular science can we actually get out of these? Well, for black holes, much like the one at the heart of our own Milky Way, it has been shown that the mass and the size of the galaxy is actually closely correlated with the mass of the supermassive black hole at its center. And so this suggests actually that black holes must influence the growth of the galaxies that they reside in, and that the largest of these massive objects will be associated with the largest galaxies that we actually observe. In addition, due to their extreme nature, they also provide us with a unique insight into various processes inaccessible to us on Earth, such as accretion under extreme conditions, formation and evolution of jets, while they can also accelerate particles up to quite high energies. And so as a consequence, they actually provide insight into a wide range of interesting physics. And so because they're so important, right, one actually really needs to work out, well, how can we actually detect black holes that are found in galaxies much further away from us? And so, well, the most direct evidence for the existence of these massive objects actually comes from the detection of an AGN, or an active galactic nuclei. And so this type of activity will actually usually present itself either through recurring luminous flare emission in multiple wavelengths, large-scale jets like this seen here in this beautiful image, or even just interesting emission lines that you detect in optical or even X-ray wavelengths when you take spectra for this. And so these are obvious because they kind of shout in the sky, right? They're like an angry toddler. They're very obvious when you look out into our night sky. However, it's actually been shown that observationally that most of the active black holes we actually detect are actually located around a redshift of about 2. While at closer redshifts to us, the number of these active black holes actually begins to drop off quite dramatically. And as we know that black holes are found at the heart of nearly all galaxies, when we go out and calculate the number of galaxies that we expect should harbor a black hole by literally counting all the galaxies we observe, we find that the number of active black holes do not match the number of supermassive black holes that we actually expect out there. However, models of black hole evolution suggest that there should exist a large number of these quiescent or quiet supermassive black holes, in which gas accretion will occur at a significantly slower rates. And as such, these population of quiescent or non-active black holes may actually be able to explain the discrepancy in our observations of why we don't see as many active black holes in a redshift closest to us. And so if these quiescent black holes are a non-negligible fraction of the whole black hole population, then how does one actually detect the black holes in these quiescent galaxies if they don't show the same properties as their more active cousins? Well, one way that we can actually do this is by studying the kinematics of the gas and stars at large distances, but that are still within the sphere of influence of the black hole itself. However, this type of technique actually requires years of data and careful analysis of individual components around the host. But more importantly, this technique is best suited for studying only the closest black holes, like what was done for the stars directly surrounding Sagittarius A star, or what won the Nobel Prize recently. But if you actually try to go to further galaxies, this study becomes increasingly more difficult for these more distant galaxies, because the angular extent that we actually need to resolve actually becomes smaller and smaller, which means you can't actually resolve the movement of the stars as well as what you could do by looking at the black hole in our backyard. However, a more direct way in which one can actually probe the properties or the existence of a black hole at the center of a quiescent host is by using tidal disruption events. So a tidal disruption event occurs when a star that is orbiting around a massive black hole approaches a black hole at a radius less than or equal to the tidal disruption radius of the black hole itself. And so at this point, the star is subjected to very strong tidal forces of the black hole, which can exceed the binding energy of the star and actually rip it apart. And so when this happens, half of the stellar debris of this now destroyed star will actually be expelled on unbound orbits and escape the black hole, while the other half will be confined to bound orbits around the black hole, which will circularize, forming an accretion disk, which will eventually be accreted onto the black hole, producing a luminous, short-lived accretion-powered flare, which is what we actually go out and try to actually detect. And so when we actually go out and look for these tidal disruption events, we find that we actually detect emission from these events. Actually, they tend to peak in optical UV or even soft X-rays. And so as a consequence, time domain surveys such as the Assassin survey, the Zwicky transient survey, Atlas, or the Young supernova experiment, which is also run out of dark, for example, these kind of surveys have dramatically kind of helped us in being able to detect and characterize the properties of these unique events, because you can actually detect a large fraction of them because of the fact that they mostly peak in optical. While high spatial and spectral resolution X-ray instruments they're in space, actually allows to kind of probe the full multi-wavelength properties or picture of these events by allowing us to also probe the accretion disk and hotter emission that can't be actually detected in the optical alone. And so as a result of this kind of unique combination of using both ground-based all-sky surveys that are located all around the Earth and also the space-based instrumentation, this has actually led to a dramatic increase in the number of events that we detect and even follow up now. However, surprisingly, we've actually seen a wide range of emission arising from these events. They just don't fall into this natural picture where they're only peaking in optical or where you actually expect there to be in X-rays. And so this has actually dramatically changed, as you can see here, between 2018 and 2020, where our kind of candidates that we actually detect now have kind of exploded, meaning that we now can kind of see differences or even some changes in the properties of what we would have expected prior to 2008 that we expect to see with the TDE. And so in particular, we find that some tidal disruption events that we actually detect emit both in optical, UV, and X-rays. And in particular, there's a canonical tidal disruption event called Assassin 14Li, which I have shown here, which in 2014 showed both the optical, UV, and X-ray bright, where the properties of this source was exactly kind of what we were expecting to try to find associated with these events. While Some other events don't, but actually the more common thing is that you actually find that other events don't seem to exhibit observable X-rays and are really only observable in optical or UV. And so here's an example here of Assassin 18PG. And this is the most common type of tidal disruption event that we detect. Seeing X-rays is usually the exception rather than the rule, right? Which is different from what our expectations were necessary. And then of course, there's even a stranger type of tidal disruption event where over the last few years, we even found that some of these events only emit in X-rays. And so this example here is called Swift J1644 plus 58. And this is there's like this one and there's like one or two extra that show only this bright X-ray decay that came from a quiescent black hole. But this is kind of a rare event. We haven't seen one since 2016, which is also interesting in asking other questions. However, the key takeaway is that even though we're just looking for a star being disrupted or eaten by a black hole, right? We notice that when we look at the demographics of our population, we find that they exhibit a wide range of observational properties, right? Where we actually see this type of, a wide variety in their emission types that we actually could search for. And so as a consequence, right, a natural question that then arises that we see this is what exactly determines whether a source will be observable in X-rays, optical or UV wavelengths when we are specifically trying to follow up or detect these in these events? And what does this actually mean about the properties of these sources themselves? Well, a hint to the origin of this kind of diversity actually comes from when we're trying to understand whether the isotropic or bolometric luminosities of these TDEs are, and determine whether they are actually consistent with what we expect from the Eddington luminosity of a black hole that is associated with the event. And so here the Eddington luminosity, just to remind everybody, is the maximum luminosity that a body can achieve when there's a balance between the forces of radiation acting outward and a gravitational force acting inwards. And so black holes will have a particular value that you can compare it to, and we can actually take what we see, the luminosity of our star or our tidal disruption event, and make a comparison specifically. And so what we have here is that we actually, on this plot where we actually have essentially the bolometric luminosity or isotropic luminosity and a kind of a proxy for the black hole mass, right? But essentially this is on the x-axis, which is essentially just the time that it takes to emit that energy. But you'll notice here that I have kind of an indication of where we expect different black hole masses to fall on this plot. And what we find is that the ones that are above, sitting up here, they are actually super Eddington events. And so these are events actually, their bolometric luminosities exceed the Eddington luminosity. And these events actually, and that's not so surprising for these events because they exhibit strong jets. So, they may be able to just exceed the Eddington luminosity without a problem because it's not the same as emitting normally. While down here, the vast majority of events that we actually detect are what we call sub-Eddington in nature. So their emission that we observe is not yet reaching what the Eddington luminosity of that particular black hole mass would actually be. But when I make this plot, what we were kind of curious about, and maybe what you notice, is that actually there seems to be a gap between these two events, or these two type of subset of events, right? And so I should note that all these events on this plot are the ones that produce X-rays. And I'll touch a little bit on the ones only that produce optical only later. But what we seem to find when we actually plotted this isotropic luminosity as kind of a function for a proxy of black hole mass, we found that they seem to exhibit this possible bimodality in which our events which have luminosities that are super Eddington compared to those that are sub Eddington are actually separated by some form of gap in that luminosity space. And so naturally, we kind of wondered whether this was just an observational bias of some form, or this was actually telling us something about the physics or properties or environment of these events themselves. And so one clue to the origin of this gap actually kind of comes from plotting the essentially the X-ray to optical luminosity ratio events, which is essentially what we've plotted here. So the X-ray luminosity is shown on the y-axis and the optical luminosity is shown on the x-axis. And so what we find is that the sub-Eddington events, they actually fall below the gap well, that actually fall below that gap that I was pointing at before. And when we plot them on this plot, we find that they actually have a ratio of approximately 1. So what that means is that they actually show nearly equal amounts of X-ray emission to optical or UV emission. While here we have the sub-Eddington events, which have an X-ray to optical ratio that is significantly larger than 1 associated with this, indicating that their emission, is dominated by the X-ray emission from these objects. And so why is this interesting? Well, this is interesting because when you look at the sub-Eddington events, which, like I said, corresponds to such a large fraction of the TDEs we detect, we find that they're actually quite highly absorbed, right? So what that means is that they actually have large column densities that are surrounding their event. So there's a lot of material, surrounding or shielding the black hole and the high energy accretion. And so what this actually implies is that there must be a large amount of material surrounding these events that actually are causing significant reprocessing, such that a large amount of optical emission is produced in addition to their detected X-ray emission, right? And so kind of this is what we were thinking about. And so as a result, this predicts that there should actually be events that would naturally populate what we call this reprocessing valley, so essentially this gap. And they actually should have luminosities and even densities, which would mean that they would show little to no X-ray emission, as it's been all reprocessed because of the large amount of material, right? And it's been reprocessed specifically into optical and UV energies, right? Or we would have seen them in this lower part of this diagram, right? And so the prediction that we have from this plot is, do optical and UV only TDEs, the ones that don't produce X-rays, do they fall into this luminosity gap that we actually see? And in fact, this is exactly the case. When we actually go and find, by essentially looking at the sample of TDE events which emit significantly in optical and UV emission, we find that they have luminosities or even densities that naturally populate this reprocessing valley, suggesting that the environment around the TDEs lead to the natural diversity in observational characteristics of TDEs detected in optical, UV, or even X-rays. And so just to make this kind of clearer, I essentially took what was this bright green bar that I showed here and just replotted here in kind of this shaded region here. And you can see that all the optical UV events sit nicely in this plot. And so in fact, this observational discovery or indication based on the demographics of these events was actually shown theoretically by the nice work by Jane Dye, who was actually also at the University of Copenhagen a few years ago. And she actually showed that this actually must be the case, that the environment and how we're viewing it actually really dramatically affects the properties we see. And so in particular, the emission properties of an event and whether it actually emits in X-rays or not depends heavily on how one views the event, at what angle you're actually viewing it. With events that exhibit no X-rays, you actually tend to be looking straight through the disk, straight through the disk this way. So you're coming from this part here. And because you have a lot of column density, because you're looking through a lot of material, we find that that tends to absorb all the X-rays. While as you go kind of off the disk, you kind of move at an angle upwards along here, you actually are now looking through less material, essentially. So you've got less reprocessing occur, which means that you can now start to get more and more X-ray emission associated with this until you look straight down the jet, where you only see X-ray emission coming from these events. And so now that we kind of have like an overview that like TDEs tend to show these vast range of observational properties, and it seems to be kind of tied together essentially with the how we view these events and also the material surrounding from this. The next question that one should ask is, well, when we're looking for these events, right, how do we expect the emission from these events to type of evolve with time, right? Because there is a kind of a prediction of what we expect and what we kind of search for when we're looking for these in transient surveys. Well, it's expected that the emission from a TDE will actually decay following a simple power law, and which is actually set by the timescale in which the stellar debris will eventually return back to pericenter, which is essentially the point of closest approach to the star of the black hole, And so if you assume kind of like a Keplerian orbit, what you find is that this timescale is expected to follow a T minus 5/3 power law. However, the exact power law that index that you would actually get depends on a number of properties, such as it depends heavily on like the evolution and physics within the accretion stream, the properties of the star itself, such as the stellar structure of the star being disrupted, or even the impact parameter of the star with the black hole, or so essentially how it interacted with the black hole itself. But on average, when we're looking out into surveys, this is what we're trying to look for. We're looking for a T-minus 5/3 decay rate that is associated with a black hole or a center of a galaxy that did not show any emission prior to that would indicate it was an active black hole. And so let's take a look at the evolution of some events to see if it actually follows this T-minus 5/3. And so here is this canonical tidal disruption event, Assassin 14 Li, that I had mentioned before. And one can see that at early times, within the first, 200 days or so, this emission from this source in optical and even in X-ray, so in all wavelengths, and even in the bolometric luminosity as well, seemed to follow a T-minus 5/3 power law decay quite nicely. What we actually expected. However, as we continue to kind of follow this event, we began to notice that the emission from this event, both in X-rays and optical, and even, like I said, the bolometric luminosity, started to kind of become significantly flatter than this T-minus 5/3 power law, indicating that the emission from this event is now not consistent with fallback at late times. So it's not consistent with the picture that I had mentioned that led us to assume this T-minus 5/3. And so we wondered whether this behavior is kind of unique to this event itself, or whether this is common in the population of TDEs. And so one can actually look at the light curves of many different tidal disruption events and actually quantify how the emission of these events look at early times compared to those at actually late times. And so this is what we did. And so what we find is that at early times, the light curves of TDEs tend to become more consistent with this, with this canonical T-minus 5/3 that is associated with fallback. And this is what's seen here by this dashed teal histogram shown here. While at late times, the emission from these events is actually much flatter than this T-minus 5/3, right? You can see that there's a shift in these two histograms. And what we actually find is that this decay rate that we're actually seeing at these late times is actually more consistent with disk emission in these properties. And so we find that this at this time, when I originally made these plots, we found that this was particularly in the X-ray properties. But since then, we've gone and looked at all the X-ray or all the optical and UV properties of these events. And we find that actually this behavior is seen in actually all wavelengths, where this effect tends to be strongest in the highest energy wavelengths, so in the X-ray and UV wavelengths. And so in particular, what this type of behavior indicates is that after a specific amount of time, fallback of the stellar debris actually kind of stops. And what you actually get is that you form a stable accretion disk that then powers the late time emission properties of these events. And so this is kind of exciting because it actually indicates that tidal disruption events allow you to watch the formation of an accretion disk in real time, right? And this is different from like an AGN, which already has an active AGN, which already has an accretion disk. So you get kind of a different picture of what's going on around a black hole. And so as a consequence, they kind of provide this powerful probe of accretion disk formation on quite a number of scales. But you'll notice that when you look at the kind of, before I said at late times, these events tend to kind of transition to kind of more flatter light curves. But the question that I kind of said is that, when I showed the first plot, I kind of just cut the light curve in half, right? But if you see this in more than one type of event, then you kind of start to wonder, well, what is actually kind of setting this transition? And so what I have plotted here is essentially the time in which we found that essentially this transition from early to late time actually occurs by fitting these light curves, and where you actually find that it's the most optimal, showed here. And this is shown in days on the y-axis, while on the x-axis here, we actually have black hole mass. And what this plot actually finds is that we find that the flattening of these light curves is actually consistent with the fallback time, where the fallback time is given by this equation shown at the top here. And to make this more obvious, I've shown that the dashed lines here shown in gray indicate the type of fallback times that we expect for these different events. And you find that the different black hole masses kind of fall nicely in this. And so it's kind of nice to see essentially this kind of picture, the fallback and the formation of the accretion disk in quite nice view altogether. So I've shown that, TDEs have all these beautiful properties. They're observationally very rich across multiple wavelengths. But what can we actually use tidal disruption events apart from being able to watch the formation of accretion disk in real time? Well, apart from shedding light on the accretion processes occurring within these events, TDE light curves actually have the potential to provide strong constraints on the black hole mass associated with each black hole. And so, as you can see here, we have this equation. We actually find is that the rise time of the multi-wavelength light curves, or what we define as the time to peak brightness, is actually very sensitive to the black hole mass. So when we have larger black holes, we find that it actually takes longer for that the emission from that tidal disruption event. It actually takes longer to rise to peak brightness compared to the smaller black holes, and it's given by this equation shown here. Okay, and you can kind of see in this plot here as well, where you've got the time on the bottom on the x-axis, and this is the essentially luminosity or just accretion, and you find that the black holes, the larger the black holes, they tend to take longer to get there. And so as a consequence, if you actually can see the early time rise to peak, right, essentially, and actually constrain that, you can get a really nice independent constraint of getting a black hole mass independently of getting, say, a spectrum, which is usually how people do this. But unfortunately, it's not always that easy to do this, right? In a lot of cases of the current known tidal disruption events, we actually tend to only begin to monitor these events or even detect them sufficiently well after the light curve of these events has either got to peak or well after peak, right? So we tend to miss this rise to peak because it kind of takes a little while. Either we're not lucky, we weren't on the sky at the time, we didn't know what it was, for example. And sometimes we just miss that rise to peak and we only see when it's very bright. And so as a consequence, we've only really been able to kind of constrain for really a handful of events, the black hole masses of these events sufficiently, using the light curves only. And so as a consequence of this, it's a lot of time is actually required to separately and independently confirm the confirmation needed to determine the black hole masses of these objects. But what we've found is that the events that we actually have detected so far tend to be consistent with black hole masses between about 10 to the 5, 10 to the 6, up to about 10 to the 7 solar masses. And so if we actually look at the black hole mass as in a galaxy scaling diagram, which I've shown here, where I've plotted all the different types of AGN and different black hole masses we have from those different types of constraints, which are given by the different colors here, we find that tidal disruption events tend to probe essentially this part of the parameter space here, right? So essentially it allows us to probe kind of this lower mass part of this diagram, which is completely missed from studying AGN themselves. But what about this part here, right? We actually are we're missing a significant fraction of data, which kind of would fall into this part at the very low part of this scaling relationship. And so why is that actually important? Well, that's important because now we can start to probe if we start probing in this part of the diagram, we can start actually probing possibly intermediate mass black holes, or black holes that have about a mass of about 10 to the 4, 10 to the 5 solar masses, and start using tidal disruption events to be able to actually do this. And so the question is that can TDEs actually be used to probe the currently not well-known properties or existence of intermediate mass black holes that are found actually in smaller galaxies? And so we actually think we can do this. We can actually take these. And so you probably know Charlotte, right, who's at Dark, right? And so Charlotte has been doing this amazing work where we actually discovered this event here called AT2020neh. And we think that this type of source will actually maybe kind of one of the kind of sources that actually kind of prove that you can actually use black hole tidal disruption events to probe intermediate black holes. And so this is a newly discovered TDE that was discovered in 2020 last year in a nearby galaxy. And, you know, Charlotte has actually been leading quite a large fraction of the follow-up associated with this event. But what we find is that this event, when you look at it, right, we find that photometrically and even spectroscopically, this event looks very much like a TDE that we know. It shows kind of the same spectral lines that we have seen in tidal disruption events, which I won't talk about today. It shows the same black hole, black body temperatures that we see in other events and what we expect. While, as shown in this plot here, the post-peak evolution is comparable to that seen from other TDEs, and it actually seems to show this canonical T-5/3 behavior that we had seen before. However, what makes this event stand out is essentially its rise to peak. Compared to the sample events, which we have constraints essentially on the rise to peak brightness of tidal disruption events, we find that AT2020neh actually rose to peak brightness within 13 days, which is 3 times faster than any other known tidal disruption event that we have so far detected from this. So remember that I showed you before, essentially, that the rise to peak of our light curves is very sensitive to the black hole mass, where larger black holes will take longer to rise to peak compared to smaller black holes. And so here is our equation. And so if we actually take essentially our 13-day rise to peak, this actually will then plug it into our equation and try to work out what the black hole mass is. This is essentially what Charlotte and even Brenna Mockler, who you may know as well, who's visited Dark a few times, or NBIA a few times, they actually find is that this corresponds to a black hole mass of about 10 to the 5 solar masses, right? Which suggests that this black hole is an intermediate mass black hole. And so this is actually particularly exciting because the detection suggests that, you know, we have identified a quiescent intermediate mass black hole. And in particular, the galaxy associated with it is a dwarf galaxy. And so dwarf galaxies actually make up the majority of galaxies that we actually see in the universe. But currently, it's actually very hard to detect black holes in these galaxies because active black holes are not very common in dwarf galaxies. However, if we actually can find a population of these 2020neh-like tidal disruption events, where you actually find TDEs that rise very quickly, this actually now provides us a nice mechanism or opportunity to identify black holes in dwarf galaxies and start to probe the intermediate mass range of black holes in our universe itself. And so this is very nice. And I should also note that we actually took a lot of other type of measurements as well, take spectra and did other kind of constraints on trying to constrain the black hole mass. And we find that it is all consistent with this intermediate mass black hole. But from the photometry, you can do this alone. So it's quite a powerful technique, especially as we start to move into LSST when we get all these many discoveries. So while I've talked about that, you know, we have this star being disrupted, I've talked about how they actually decay, what type of emission they tend to be, that we can use them to constrain the black hole mass. Well, what about the actual star, right? Remember I said that a TDE results from the tidal disruption of a star that wandered too close to a black hole and was subsequently ripped apart and then accreted. Right? Usually when we're considering the physics and trying to understand it from that concept, we can just usually assume that it's a main sequence star of about 1 solar mass and that's been disrupted. And we do this for simplicity, honestly. But actually there is a way we can actually start to constrain the type of stars that were actually disrupted from these events. Right? And this is a nice trick that Brenna Mockler actually put together quite recently. And so apart from being able to constrain the masses of black holes, models of tidal disruption event light curves can actually be used to estimate the parameters of the disruption. And so what that means is essentially you can estimate the mass of the star, the efficiency of the conversion from accreted mass into observed luminosity, for example. However, when modeling these light curves, one finds that even though TDEs have an efficiency similar to those of AGN, for example, there's actually kind of a large degeneracy, should I say, between the efficiency of that conversion of mass into energy, which goes into luminosity essentially, and the mass of the disrupted star that we actually see here. And so for us to also be able to constrain the properties of the star itself, right, or the nature of the disrupted stars, we actually kind of need to break this degeneracy that we actually see between essentially the efficiency and the mass of the star in this plot. And so if we can actually do this, this actually provides us with invaluable insight into the dynamical processes operating in galactic nuclei, and also allow us to start probing the properties of the stellar populations very close to black holes in galaxies very far away. So it's kind of this very nice thing that can be quite encompassing. And so assuming that the emitted gas associated with a TDE originates from this stellar debris, the mass and evolutionary state of this disrupted star can be constrained independently using information from both the light curves and also the spectra associated with these events. And so in particular, we can actually take measurements of nitrogen to carbon as measured using UV spectra using the Hubble telescope. And these are particularly useful for estimating essentially the corresponding abundances in the emitted stellar debris that's been disrupted, essentially because nitrogen and carbon lines actually have this, especially in UV, should I say, actually have similar critical densities and excitation energies and involve ions that have similar ionization energies. And so what people have done is that they've searched for these lines and they've actually measured these lines and found that the TDE debris is actually incredibly nitrogen rich, which seems to hint towards the fact that TDEs may result from kind of evolved stars. But they couldn't really go the next step further, right? They said, we found these incredibly rich events, probably from an evolved star. What does this mean? And so in particular, we can actually now kind of test this property. And so Brenna Mockler, who is at University of California, Santa Cruz, kind of decided to look at this TDE sample, whose spectra all have relatively high nitrogen to carbon abundance ratios. And so what she did was essentially estimate the location of the nitrogen-rich stellar debris by essentially deriving the equivalent line widths of the nitrogen lines that we detected in optical emission. So this is just for an example of these type of lines that we did this. And essentially, these are the radii that you can get from these spectra. And so what she did is that once she had these essentially where this material is based on the optical spectrum, she then compared this to the derived location that is expected for location of the debris from the disrupted star as derived from the light curves, in order to kind of show whether or not this emitting gas could actually originate from this undigested stellar matter as opposed to, say, pre-flaring material, for example. And so what she found is that the nitrogen lines appear to originate in the photosphere radius and essentially the wind radius associated. So you might have a wind, like an outflow associated with your event, but essentially you find that there's kind of in between this. And this is kind of exactly where we expect the material of the disrupted star to be, right? So this is great. This is exactly on the right path that we expect. I should say that it's now not in prep, it's actually now on archive, actually. And so now we know kind of that this nitrogen material is associated with the stellar debris. Brenna was actually able to kind of use this constraint on the nitrogen to carbon ratio that was derived from the UV spectra from those other TDEs, and actually kind of place constraints on the nitrogen to carbon composition of the stellar debris associated with different TDEs. And this actually allows you to kind of constrain the masses of the disrupted stars. And so what we've kind of plotted here is essentially the stellar mass that is shown on the bottom here, which is actually essentially a function of the fallback debris composition, or essentially the nitrogen to carbon abundance ratio, which we kind of have here. And this is for a main sequence star at a range of stellar masses and ages. While the gray shaded region corresponds to kind of the nitrogen to carbon ratio derived for different TDEs using their UV spectra. So that's what we get on constraints from here. And so from this analysis, what Brenna finds is essentially that the minimum stellar mass that can produce such an enhanced nitrogen to carbon ratio is actually a 1.3 solar masses, right? So that's the minimum mass that you actually need. So it's actually slightly higher than what we actually usually assume. And so as seen here by the lines that are also plotted on here, which actually kind of represent ages of the stars that we actually have, we find that for them to be able to produce this ratio, that those stars that have masses around, close to this 1.3 solar masses would actually need to be quite old. They would need to be kind of close to the end of their main sequence lifetime to have such an enhanced ratio, right? They need to kind of be in this range here from that. And so this kind of seems to suggest that the event that the stars that are being disrupted by these tend to be relatively more massive than we expected, so intermediately massive, and they tend to be more older than, they tend to be reasonably old. And so, like I said, this kind of provides a nice way to kind of even probe the stellar populations close to the nuclei of these galaxies. And so, now that I've kind of touched on like using what TDEs look like, what we can use them for, right? You'll notice that I had mentioned previously that TDEs are associated with quiescent galaxies or quiet galaxies, and that they harbor a black hole. And so your probably question is, well, we don't really understand the duty cycles of AGN. And we may have just missed, for example, a galaxy going off as an AGN and it's gone quiet again, for example. And so then really one has to kind of wonder is like, how can we start to differentiate TDEs from active galactic nuclei or galaxies that are expected to show an active loud black hole? How we confirm that what we're actually seeing is actually from a TDE, not just some AGN emission that actually comes from this. And so here I'll specifically talk about photometrically being able to kind of differentiate this. But this is, of course, a big question that we are trying to kind of hunt. And I think it's still not completely clear how we actually differentiate these. But there are some hints towards this. And so it's actually been shown by a number of studies that TDEs actually kind of power low luminosity AGN. And so as a consequence, we actually think that TDEs can contribute significantly, for example, to the luminosity function of AGNs in multiple wavelengths. And so because of this fact, as I said before, it's a major challenge in TDE studies is to efficiently and cleanly select TDEs from that of AGN or even other transients, because type 1As can kind of look a little bit similar as well, and some 2Ns as well, but that's another discussion. But in particular, we want to be able to cleanly select these without requiring significant resources and observational time to follow up each potential candidate. And so this is particularly important, as I said, when we move into the Rubin era, where we're going to have hundreds and thousands, huge amount of transients, but not enough of spectra to be able to, spectral capabilities to be able to follow them up. And so it's really important to kind of start thinking of sets of observational methods or characteristics that can kind of help improve the credibility of an unknown transient being classified as a TDE before, essentially before we can extensionally follow it up, right? To really help us kind of filter through this, because we really want to be able to maximize what we can do when Vera Rubin actually turns on. And so while spectra is kind of the main way that we actually do it, right, it's observationally expensive. And so one way we can actually try to do this is by its photometry. And so in particular, we can look at essentially what we call the color or how soft the emission of these events are and compare that to AGN. And so this is what we essentially did here, where we essentially have what we call the hardness ratio, where you're very hard at the top here and very soft. So think more thermal emission on the bottom, more non-thermal emission on the top. And this in particular is in X-rays, but we do see some similarities also in optical and UV behaviors. But what we find is that essentially TDEs show little to no variation in their color or their softness or hardness ratio during the decay of their flare. So as the flare brightens and decays, it tends to be relatively constant with time in X-rays. And this is actually quite in stark contrast to that of AGN, which actually show quite a lot more variation in emission in those sorts, like the AGN. But AGN tend to become softer when they become brighter, and as they become fainter, they become harder in emission. And TDEs don't show that; they're constant in their color and their temperature, and essentially their softness. However, the problem is with X-ray is that it's harder to do this, right? Because usually X-rays are done as a kind of an afterthought in a lot of ways. And like I said, not every TDE actually produces X-ray emission. And so we have to kind of think of other ways to really separate them. And so probably a more promising approach, especially in the Vera Rubin era, where one may not have as much color information, we can actually kind of now start looking at how variable their multi-wavelength light curves are. And so what we do is essentially that AGN, for example, their emission can actually be described by something called a damped random walk. And we can actually see if we can compare essentially how variable these events tend to be compared to AGN under that type of behavior, if you're assuming if it's like something that's a damped random walk or not. And so here, this is what I did essentially with the X-ray emission for this, and I'm currently also trying this with the optical UV. And what we find is that essentially our sample of AGN are showed here by the orange light curve. And you can see essentially our TDE sample, which is shown in green, is much less variable than the AGN one from here. And then we have this kind of overlap of what we call TDE AGN candidates, where it's not entirely clear where they fall, because we actually get these kind of what we call ANTs, or anonymous nuclear transients now, that kind of have properties of both worlds. But essentially now, if you can look from the variability just based on this over the light curve, you may actually be able to start separating these events from each other. And so in particular here, like I said, TDEs tend to be less variable than those of AGN, of similar or even larger masses that we actually observe. We can also look at kind of their variability times, or their variability timescales, so how much they change over their timescale and how bright they tend to, or how much that variability tends to be. And what we find here essentially is that TDEs tend to have the variability over a larger time scale that I show here, while AGN show more smaller variability, while essentially the time scale over which TDEs do that, it's over much shorter characteristic time scale than TDEs. So TDEs go off and then decay, right? And it's a very large change in brightness or luminosity, while AGNs can show smaller variations over time, but over a much larger period. So you can start separating these events. And so, like I said, TDEs show larger variations over shorter timescales type of thing. And so, this is still preliminary work, and we're looking into kind of understanding this, but this seems to be kind of like a nice way that we can start applying this to our populations of events that we actually see this, and really start working out whether something that we're actually observing is consistent with the TDE or not, which would actually help us kind of further strengthen the classification of these events as actually being a star being disrupted compared to a normal AGN. And so on this, right, I'll leave kind of the conclusions here, but essentially TDEs are a multi-wave phenomena that have a diversity in properties, and that kind of is related to the environment, but also how we do this. And really how they evolve and their light curves actually kind of imprint on them both how the accretion disk is forming essentially, and the evolution of that accretion essentially onto the black hole. And in particular, we can actually use those light curves to probe black hole masses. And so TDEs seem to be coming from moderately massive stars that are close to the end of their life. And so it'll be interesting to see if, as we get more and more candidates, whether this is actually consistent with the population. And unfortunately, AGN activity can mimic TDEs, but there are ways that we can try to pin them to separate them, and something that we're looking forward to doing, especially as we go into the next era of transient domain astronomy with Vera Rubin coming up. So thank you.
Thank you so much, Katie. This was wonderful. I really enjoyed it. I have a few questions, but first I want to ask the audience if they have some. Irene has one.
Yes, I have two actually. So thanks, Katie. It was a very nice overview. So I have two questions. The first one is about this plot that you showed with this reprocessing valley. And I was wondering, so somehow it doesn't add up for me, because you have like the adding luminosity, which is a property of the source, and then you were talking about reprocessing, which is somehow a property of the environment. So can you comment on why exactly we have this green band? Yeah, in this, but this green band exactly where we have it?
So
and like, how do we connect the properties of the medium to the properties of the source itself?
yeah, so this is a good question. So how we're measuring the properties of the medium is from the X-ray properties. So essentially you can put a constraint essentially on the column density surrounding that event. So you've got a measure essentially of this as well. And so then the question that you had is like, how does it connect to the Eddington luminosity? Well, it's not necessarily connected in the way that I think maybe I misspoke for you to kind of say that. It's just saying that like all we needed to know is that they're not super Eddington. So that implies that if there's not a jet there, that it seems to suggest that actually you can that the material is not actually has to affect the environment, affect the properties of these events, right? So the Eddington luminosity is tied by the accretion, but we're saying what happens when you take essentially this very bright, intense accretion and put it through a dense material, which we can take as a constraint. We find that actually they tend to have bolometric luminosities that would have to be kind of consistent with this picture, that there has to be this reprocessing valley that separate kind of these very super Eddington ones where they don't care, right? It's a jet, it will go through whatever it wants, compared to ones that don't have this. So all the ones that here are falling in here are these sub Eddington ones. So none of them are reaching Eddington luminosities.
Okay, I see, thanks. And then the other question is about this work by Brenna. So I was wondering, do we actually understand why somehow more massive stars are the ones that are then going, these people. So yes, in this plot, do we understand why it's more likely for massive stars to undergo tidal disruption events? It's like a kind of a gravitational events, or like, because the stars are older, so they are not necessarily more massive. So yeah, can you comment on the theory behind this?
Yeah, so I can't remember, we had like a few suggestions in the paper, and like half of them, some of them are escaping me right now, but essentially TDEs tend to be found in these E+A galaxies, which is essentially post-starburst galaxies, and they tend to be quite messy. Essentially, is that you're actually kind of mixing up they're post-merger galaxies, and so they essentially, you've had a galaxy that has been disrupted completely, but their galaxies are relatively oldish, right? So you've got this kind of more evolved population, and so you might actually have that because you have this messing up of everything close to your black hole, because you have this these extreme galaxies, you actually can now start to kind of throw stars on like certain orbits that can then be unlucky enough to get close to the black hole itself. And so it's kind of a property essentially of, I think, the host galaxy, the fact that they're found in these post-merger galaxies, which are very rare. They're only like 1% of all galaxies, but a large fraction of TDEs tend to be found in that. We also had a few other reasons why it could be, but at the moment I just can't remember exactly what else we put in there. But it's on the page. Like I said, I made a mistake. It's on archive now, actually, and I think it's accepted as a few days ago or something. Like this.
Okay, I will have a look then. Yeah, thanks a lot.
No problem.
We have a question from Clement. Clement,
yes.
Yeah.
Yeah, I have one question that's related to the previous question. So you mentioned that from this nitrogen to carbon ratio, you can put a lower limit on the mass of the star that's getting disrupted. Is it possible with the same technique or another technique to also put an upper limit, say, be sure that the mass is less than 10 solar masses or something like that?
Good question. We were trying to think of a way to do this, and we didn't really get that far, actually. But there probably is. And actually, I think when we do have a TDE meeting like we were going to, then I think maybe we should talk about seeing how to do that. But I don't know off the top of my head of how one can do this, because this comes from the spectra, so from like that constraint. So maybe you can somehow we can invert it, for example, to make that statement. But it's a good question. I actually don't know exactly. We were thinking and we couldn't break that yet, but we'd love to hear an idea on it. But it's a good idea.
Yeah. All right. Thanks.
So I have one question, and it's about jetted TDEs. Do we know if all of the TDEs have a jet and some are choked and some break through, or do you need special conditions for the jet to appear?
I guess it depends on who you're talking about and if you believe the neutrino discovery is associated with the TDEs or not.
Let's have your take on it then.
Okay, so for the ones that have neutrino associated with it, I am a bit puzzled about why you can have a neutrino associated with these events like 150 days or more after the peak brightness of the event. It's very difficult for me to understand why, and also why those particular TDEs are not, why did we not see this consistently across the population, right? The TDEs that happen to be there, they're not, I wouldn't say they're any unique. They're not like, they're just like a stock standard TDE in some way, right? In that. So that's kind of a puzzle. But of course, like, do you actually have a jet? So I think it's hard to know for these ones because I think it depends on how much material there is, right, around the thing and whether we can actually separate this, which requires kind of X-ray observations. And the thing is that you don't get enough constraint in the ranges I would expect. So you expect it in kind of like high energy, hard X-rays. Can you actually constrain this? But this is actually an interesting question. Can you use the upper limits to put constraint on this? I think maybe we had spoken about that a while ago, Maurizio, and we should get back to it now that there's more events. But I think we haven't really touched on that, actually. I think we're just kind of still at the thing that it's some material that's getting thrown out that kind of forms some bubble around your star. But I think because it's not as common to see these jetted events are very rare, that people are not thinking about that as much. But that's actually kind of, I think now we have quite a number of events that have constraints on the X-rays, and maybe this is something we should look into.
That sounds good. And another question that I had is, how well do we know the redshift evolution of TDEs, or TDE rate, I should say? Or how badly?
Oh, good question. So most TDEs tend to be about like up to like up to about 0.1, redshift of 0.1. Most are less than this. They're about 0.05 for a redshift. The ones that are jetted tend to be about 1.4, something like this, but we've only seen a handful of them. So in terms of understanding their evolution, I think we don't really have very much of an idea, I would say. Yeah, I think we don't have a strong constraint, but most of them tend to be kind of very nearby. They're about, like I said, no more than like 0.08, 0.1 redshift from there. But it's a good question. I don't think I know the answer to that one.
That's perfectly fine. Yeah, thank you. And I see, Clement, you have another hand. Is that your old hand up?
Oh, sorry, I just forgot to put my hand
then
down.
that's fine. So do we have any other question from the audience? I don't see any at the moment. So in that case, Katie, thank you so very much. This was wonderful.
Thank you. Yeah, no, thank you for inviting me. It was great.
Thank you for staying up so late for this. All right, and I hope to see you in person soon. And everybody, as I said at the beginning, this was the last seminar, the Astroparticle seminar for the year, and we restart early next year. So thanks, Katie, thanks everybody, and happy holidays.
See you.
Bye.
Happy holidays.
Bye.